To understand how interest rates evolve, we start with Model 1. This is the simplest framework for predicting the movement of short-term rates. It assumes there is no drift, meaning there is no automatic upward or downward trend over time. Instead, the rate follows a random walk, where the change, denoted as dr, is calculated by multiplying the annual volatility, sigma, by a random variable, dw. This random variable follows a normal distribution with a mean of 0 and a standard deviation equal to the square root of the time interval, dt. Let's look at a practical example. Imagine our current interest rate is 4% and the annual volatility is 1.80%. If we want to see the change over 1 month, our time interval, dt, is 1 divided by 12. First, we find the standard deviation of our random variable by taking the square root of 1/12, which is 0.2887. If the market gives us a random shock value for dw of 0.35, we calculate the change. 1.80% times 0.35 equals 0.63%. Adding this to our starting point, our new rate after 1 month is 4.63%. We can visualize these possibilities using a recombining binomial tree. In this model, every step has an equal 50% probability of moving up or moving down. The size of that jump is determined by the formula, sigma times the square root of dt. Because the tree is recombining, an upward move followed by a downward move brings us back to the same middle point. In fact, because there is no drift, that middle node after 2 periods will always land exactly back at our initial starting rate. One significant drawback of using a normal distribution is the mathematical possibility of negative interest rates. While lending $100 and receiving less than 100 back doesn't make much economic sense, the model's math allows it. This problem gets worse over long time horizons or in low-rate environments. To fix this, analysts either force negative rates to stay at 0, effectively creating a floor, or they switch to different distributions, like log normal, which are physically incapable of dropping below 0. So, how effective is Model 1? While it's a great starting point, it has limitations. It often predicts a downward-sloping yield curve that doesn't match reality, and it assumes volatility is flat across all time periods, missing the hump-shaped volatility we actually see in the markets. Finally, it implies that any change in the short-term rate causes a perfect parallel shift in the entire yield curve, a simplification that rarely happens in the complex world of finance.